Okay. Great. Thank you. Hi, welcome. I'm Michael, and I will give you an update on AllBert EinStein creating a fireball with an artificial meteoroid. Well, and we have given already a few years ago a presentation about this, Max Wolf and me. So when I applied to this presentation, I thought 10 minutes are enough. But then I realized, oh, wait, there might be people who have never heard of the project. And for all those who have heard of it, you know, there were many social events and a lot of beer in between, so maybe no one remembers. So therefore, I have to speed a bit up, unfortunately, because 10 minutes might be a bit too short. Anyway, it's very important for today's presentation to mention it. Koschny, for example, and a lot of students, they help as well. Well, not just helping, they're doing the actual work. Okay, so some background. We like to observe meteors, and of course, the question arises, what do we see? Like, what kind of meteoroid was the course of the meteor? So we would like to know what was the mass of the object. And there is this nice formula. Pointer. So there is the nice formula. So using the entrance velocity and using the emitted light, we can get the mass. The thing is, there is this tiny thing here, the luminous efficiency, which describes how much energy, kinetic energy, is converted to the visible light. And the thing with the luminous efficiency is it's difficult. Difficult situation. So Drosshagen et al., they summarized basically very nice in their paper. So they looked up different values from different authors. And as you see sometimes, like we're starting here 10 to 0, 10 to minus 8, but it's like in the same range here. So it's just difficult. So it would be great to get more knowledge about the luminous efficiency. So how to do this? The problem is, well, to get this factor or information about it, it would be great to have the mass, which we don't have. So what to do? And here AllBert EinStein comes into play, because what we want to do is we want to send an artificial meteoroid, which we exactly characterized. We want to send it to space with a rocket. So we have a rocket launch with our artificial meteoroids. Meteoroids, they are in space, and then all the other payload is deployed. Well, a rocket is very expensive, so we can't buy it just for us. So we most likely it's a shared mission. So all the other payload is deployed, and we stay on the upper stage. And only after the deorbit burn, because we want to avoid space debris, only after the deorbit burn, we separate from the upper stage, which means we are on a re-entry trajectory and a known re-entry trajectory. That's important. And then we have the entry, we get a fireball, and then we're gonna observe it. That's the plan. So how does the payload exactly look like? So we want to launch 4 artificial meteoroids. So 2 of them with a size of 9 centimeters in diameter, 2 with 5 centimeters, and for both sizes, iron and some stone, most likely some basaltic material. And the problem with round objects is, right, you need to put them somehow onto a rocket, and which is not the best shape, to be honest. So we need some kind of a structure to really hold them fixed in place during the launch. And we came up with this design. So it's basically separate elements. They are not connected in any sense, so it's just stacked together. And then like a typical CubeSat, so if for the people who are not really into this, this is like a standardized size or type of satellite. And it looks very similar to what we've done by purpose. So we basically put everything into one of those commercial CubeSat dispensers, so into one of those. And of course, since it's the same shape, it perfectly fits. You can buy one of those, put them on a rocket, and then you close the lid. It's perfectly fixed. Once it's in space or on a re-entry trajectory, you open the lid, a spring pushes everything out, and we have our objects in, well, on a re-entry trajectory. Since they are just stacked together, they will separate sooner or later, latest, of course, when the atmosphere starts acting, and we have our free-floating individual objects, which we can then observe. That's at least the plan. So, as I said, I skipped the science part. Please look up one of the older presentations. And I will go more into a different topic, because usually people say like, oh, okay, awesome science. But then there are a few people like, oh, isn't this dangerous? And of course, like, we had a look at this. And what we did is the following. So we used a software called Drama. It's from ESA, and it's mainly designed to simulate re-entries or space debris. So more, yeah, satellites. So metallic objects, thin sheets of metal, and so on. So that's important to keep in mind. So what we did here is we used this kind of model, which looks a bit different from the other model you've seen before, due to reasons I won't go into detail here. So, but it works out in the end. So we have this model, and we simulate it, and we just look at the aluminum structure. And we see that at a height of, well, between 190, we see that it breaks apart. And then latest from 90 to 80, something in this range, it completely demises. So from the aluminum, there won't be anything coming down. We don't expect anything. So no danger from the aluminum and from the structure. But what about the meteoroids, the actual objects? So we did also several tests here for the controlled re-entry, and we chose here an example re-entry trajectory somewhere between Australia and New Zealand, which is a quite reasonable place. And so we did the same simulation with Drama, but keep in mind here, like, we are now simulating not just like thin aluminum, but massive massive spheres of, well, rock. So that's basically what we are targeting for. So 15 joule would be perfect, because this is considered as no problem at all. And for 3 of them, we see, well, we have lower joules, but for the basalt one, we see a higher value. But very important here, 3 things to keep in mind. The first, well, that software was not designed for this kind of object. So things like a breakup of the material, this is not considered at all. The next thing is, we are, like, there's a purpose why we are here somewhere over the ocean, or like somewhere in between Australia and New Zealand, because there is nothing. So if something is left, we don't hit anything, right? And there have been other spacecrafts, for example, the ATV, Automatic Transfer Vehicle, I think, from ESA, or even the Mir space station, they deorbited somewhere. And, well, I don't know for sure, but I could imagine that something was left, but it was somewhere over the ocean, so no one cared. So that's the next thing. And the last point to consider here, well, there is a natural background flux, right? And so 9-centimeter sphere, it's not too big, so we don't read people get hit all the time by meteorites. So I think we have to set this value basically into a context, so there is not really an actual danger here. We have done this for different cases. What happens if the deployment mechanism doesn't work? What happens if the orbit is too strong? Whatever, if the overburn is a bit later, and so on. And basically all the results are very, very similar. So going into the same direction. So therefore, I don't show them here. That was the re-entry. But also another point to consider is the launch. We have to go somehow up. And here we did the following. We did a FEM simulation. And in this simulation, so we created this very nice model of a thin plate model, modeling the spheres as just point masses connected to the outside structure. And then we did different tests. We did a quasi-static simulation, so with a force of 1000 Newton, and we did random vibration analysis. And for those, you get really pretty pictures all the time with nice colors. And for, I think this one is for the random vibration analysis. So we see here at those edges, we get some peaks. But those peaks, they are just, I talked to a colleague of mine who's really an expert in this. And he was like, that's an artifact from the simulation, so we don't have to worry here. But anyways, if we take those peaks, which are then in the end 28 megapascal or 52 megapascal, and we compare it to the fatigue strength and yield strength of the aluminum, we see that those strengths are way higher. So even taking a safety factor of 1.25 or something into account, we are far from breaking the aluminum. So we are fine. Another point to consider is the eigenfrequency, so that once it's in a rocket, it doesn't start dancing around and breaking. So we have to be higher than 130 hertz, and we are with the first eigenmode at 990 hertz, which is also fine. So everything great, right? No, unfortunately not, because this is just a simulation. What you actually need is a real test, and that's what we are right now on. We are doing qualification with a scaled, so it's really a tiny piece, a scaled model, and it looks very similar. It's just a 5 centimeter sphere. It's, as I said, stacked together. We put this into a box and on a shaker to get actual data. And the outlook is then, after we are done with the shaker tests of the scaled and the FEM simulation, we go for the real big model, like the real one, to do the same tests again. Then we need some funding, so if someone has some money left. And then we have the launch, and we create our artificial, or our real meteor with our artificial meteoroid. That's the plan. Thank you very much.
Thank you so much. We have time for one quick question.
What will be the entry speed of the meteors?
That's a very good point. Obviously, since we are in orbit, we have not the typical entry speed of a meteoroid. We have lower entry velocities, I think something like 8 kilometers. So, but that's actually the best we can reach right now. Of course, it would be great if, you know, we do some moon slingshots and get high. But let's start with this one. If we show that it works out, no one knows what the future brings.
Thank you so much once again,
Yeah,
Michael, thank you.
Just come to me then later.
Yes.